Okay, so here is our warm-up. Today we are learning about circles. And we have a restaurant which is replacing circle tables with square tables. They need to have the same area. And we're given the circumference to be 4.1 meters. So we're going to use our circumference formula. And we're going to substitute 4.1 meters for the circumference. And we'll solve for the radius this way by dividing by 2 pi. One thing you need to remember, when you divide by a product on your calculator, make sure you put parentheses around it. And if you do that, then you should get that the radius is about 0.653 meters. So then you can use that in your area formula to find the area of your circular tables. So the area is going to use pi r squared, and it's going to be pi times your radius squared. Oops. But what would be good is if you saved your answer to this in your calculator so you had a more exact answer than just 0.653. And when you do that, you should get that the area is about 1.34 square meters. So that's the area of your circle table. Now you're going to get a square table, and you want that square table to have the same area. So remember that the area of a square is just side squared. And so the area is 1.34. And if you square root, remember you only want the positive answer, so your side is 1.16 meters. So when we're solving circles, you'll be using two formulas. You'll be using your circumference formula and your area formula. All right, and we'll be talking today about arcs and sectors. So an arc is a part of the circle which joins any 2 points. So if you imagined that your circle was a pizza, the arc would be just the crust of one piece of that pizza. It literally says the arc is a part of the circle which joins any 2 different points, and it can be measured using the angle theta subtended by the points in the center. To find the length of the arc, it's just a fraction of the circumference. So the whole circumference is 2 pi r. And so in this case, we have theta degrees of the circle out of a whole 360 degrees in the circle. And so that fraction, multiply it by your circumference formula, and it will give you the length of this piece. A sector is like the whole slice of pizza, not just the crust. So the sector is the region between 2 radii of the circle and the arc between them. And to find the sector area, it's really the same idea. Find the area of the whole circle with pi r squared, and then multiply that by the fraction, theta degrees, whatever this is, divided by the whole circle of 360 degrees. All right, so in number 1, we're going to find the length of the arc. And so we're going to be using our circumference formula, 2 pi r, and we're going to multiply it by the fraction of the circle we have. So we have 48 degrees out of 360 total in the circle times, and then your circumference formula is 2 pi r, so it would be 2 pi times the radius of the circle, which is 3 centimeters. Okay, and so you'll multiply that on your calculator, and you should get that it's about 2.51 centimeters. To find the perimeter of the sector, we have to add up all the sides of that piece of pizza. So I know that this over here is 2.51. This one is 3, and this is marked congruent, so that would also be 3. So we just add them up. And that should give me 8.51 centimeters. To find the area of the sector, you're going to use the same fraction, 48 over 360, but multiply it by the area of the whole circle. So 48 out of 360, that's the portion of the circle we have, times the area, which is pi r squared. So pi times 3 squared. And if you put that in your calculator, you should get about 3.77 square centimeters. All right, so we are on now to a more theoretical problem about Belinda and a lampshade. All right, so if you were to fold up or make a circle out of this shape here, it would look like a lampshade. The area of this lampshade is 0.32 square meters, and the length of the shorter arc is 1 meter. It has a slant height here of 28 centimeters. And remember that the conversion from centimeters to meters is to divide by 100. So that would give you 0.28 meters here. And now we have the same unit on everything. So they're telling you that this came out of a big circle where we cut out the middle circle. So we had something like this. We cut out the middle circle. And then we cut on 2 points like that, 2 lines like that. So this is the piece that we're looking at. So the first thing we want to do is consider the area of the big circle minus the area of the small circle to kind of get this donut shape here. And then out of that donut shape, we have theta degrees, which is not super specific, but that's how it's marked. So we have theta degrees altogether. Out of, in a circle, there's 360 degrees. And then we're going to multiply that times the area of the big circle minus the area of the small circle to find the area of this donut shape. So I'll say area big circle minus area small circle. Okay, so the area of a circle is pi r squared, and the radius of the big circle is marked big R, and the radius of the small circle is marked small r. But if I look at what I'm trying to show here, it's only in terms of small r. So there must be a way I can represent this big R in terms of small r, and there is. The big R, it's equal to small r plus this piece right here, which I happen to know is 0.28 meters. So plus 0.28. So let's go back over here. The area of the big one would be pi big R squared, but I'm going to substitute in little r plus 0.28 for my big R. So it's pi times r plus 0.28 squared. Minus the area of the small circle is pi little r squared. Like that. And now we need to simplify this. So I'm going to have to square this binomial here. And when I do that, I'm going to get r squared plus, let's see, 0.28r and 0.28r is going to give me 0.56r plus the square of 0.28. And I'm just going to write that as the square of 0.28 for now because I think I'm going to be able to do something with that. And then, oops, I should have minus this here. Let's forget that. Minus pi r squared, and then close it. Okay, and what I'm going to do next is distribute the pi, because it's going to give me a pi r squared, which will cancel with my negative pi r squared. And actually, this was here, wasn't it? So keep my theta over 360. Pi r squared plus 0.56 pi r plus pi times 0.28 squared, and then minus pi r squared. And the reason I had that all written out is so that I can cancel out my pi r squares, which simplifies things just a little bit. Like that. All right, so let's look now at what I'm trying to make out of this. The pi should be factored out, and it looks like because I only have these two terms, I can factor out the pi. Also, you'll notice here I have theta over 360, but here I have 0.28 theta over 360, so that means I should be able to factor out a 0.28 as well. So I'm going to factor out 0.28 pi like that. And then that's going to come to the outside. So the 0.28, I'll put it here because that's how they have it. The pi, I'll take it in front here. And then this is going to give me 2r plus, and the pi's cancel. One of the 0.28's cancel, but I still have another 0.28. And let's see, this matches, this matches, this matches, and that's just my unit square meters.